10th lecture in dynamics, and we have finished all of the material in chapters 11, 12, and the primer on orbital mechanics, and all the homework has been assigned. So what remains for us are the homework, which should be submitted today or over the weekend, and the quiz that's over chapters 11 and 12. Now, it says that the quiz is due no later than September 13th, but it'll be open for longer than that. So, and there won't be any penalty for late submissions. So, today, I just kind of wanted to talk about that idea that, first of all, there is no new material. Second of all, that the homework is all posted and the quiz is ready to go. So aside from that, all we're going to do is talk about problem completion. So I was going to take questions from the students. Logan, what would you like to start with?
Let's do 12.67.
12.67. All right. 12.67. Let me get it here. All right. Okay, so 12.67. Oh, it's back here. Got it. Okay, we have, did I really assign that? Okay, we have an advanced spatial disorientation trainer is programmed to only rotate and translate in the horizontal plane. The pilot's location is defined by this. So this is our R, and this is our theta, expressed in feet, radians, and seconds. Determine the radial and transverse components of the force exerted on the 175-pound pilot at t is equal to 3 seconds. Okay, so first of all, we're going to be talking about radial, transverse components, right? And we know that force in the E sub r direction is equal to mass times acceleration in the E sub r direction. And that force in the tangential direction is equal to mass times acceleration in the tangential direction. Okay, so the first thing that we need to do is to get our equations for the acceleration and the acceleration and the in both of those two directions. So, and you know, there's really, I mean, you can draw this, I guess, but I'm not really sure that we're going to have to do that. So when we take a look at we have equations for R. R is 8 times 1 minus e to the negative t. And theta is 2. Okay, so that is in the denominator. The whole thing is the denominator. 2 over pi sine pi over 2 times t. Right. And so in order to find the acceleration in these directions, we have to go back to those basic equations for, we need to find r dot, r double dot, theta dot, and theta double dot. Okay, so since the force in this direction is equal to that, we're told that the pilot weighs 175 pounds. So that means that his mass using force is equal to mass times acceleration, or weight is equal to mass times gravity. His mass is going to be his weight over the gravitational acceleration in slugs, or we could just keep it in 175 pounds per 32.2 feet per second squared. Okay? So, we need to do our first and second derivatives of r and theta. So if we look at this, and I need a little help with this when I do my derivatives, but r dot turns out to be 8 e to the negative t, and that's going to be in feet per second. This is going to be in feet, of course. Then when we take the second derivative of this, all we have is the negative comes out, so we have negative 8 e to the negative t feet per second squared. Okay, so there's our first and second derivatives. Now when I take the first derivative of theta, this is actually, you could think of this as being 2 over pi as a constant times the sine of pi over 2t to the negative 1 power. Okay? And then you may need a math table if you're not quite familiar with that, as I am not. I need to always get that value and make sure I'm not doing it incorrectly. But so we have this is our value of theta dot, and that is going to be in radians per second. And when we take the derivative of this, we're going to get negative pi over 2 times the sine of pi over 2t, and that's going to be in radians per second squared. Yes, sir?
So the sine of pi over 2t is for sure in the denominator? I wasn't sure if like
Well, that's what I'm reading it to be, but it's weird, isn't it?
Yeah.
So, okay, the reason that and we would have to check to make sure that these, I'm sorry, I'm pointing at my screen and you can't see that. I would double check on this, but I believe that the sine differentiates to the minus cosine. And so then there's a minus here. So I believe that that is correct. The other thing that leads me, maybe it's not. I was going to say, no, because if you differentiate, it should be to the minus 2, wouldn't it? So is that in the numerator then? The reason that I suspected it was in the denominator is because this value would be in radians per second. So I was kind of expecting this to come out in the denominator, but that can be taken up in the whole thing. It's weird to have t in the numerator when the seconds is in the denominator. Do you see what I'm saying? That just means that it's sucked up somewhere. I don't like it. I don't like it. But I guess the way that we would have to chase this down is to go to a table of derivatives. And let me see here. See if I can find something that will be more instructive. First derivative of sine of x. Okay, is that where I am? Okay, so let's take a look. The first derivative of sine is, oh, you can't see that, sorry. See, I would have to tell you the truth, I would have to get a, okay, so sine, the first derivative of sine is cosine. So that kind of looks more to me like this is in the numerator, doesn't it? Is that what you would say? Because, yeah, and when it comes down here, yeah, so, yeah, I'm going to say that's true. So let's do this. Let's do this, okay? So this is not true. Let's just leave it like this, okay? So then this would be correct. Oops, you can't see it again, sorry. This would be correct for this function. So it is in the numerator, and then this would be correct because the first derivative of cosine is going to be negative sine. So that all flows. All right? So far so good? Okay, thank you for your help. Like I said, whenever I do things like that, it is not to be cute in any way. It's because I really don't know. All right, so now what we need to do is to do the summation of forces in that radial direction is equal to the mass of the astronaut times the acceleration in the radial direction. And when we go back to our equations, we know that the acceleration in the radial direction is that function in your book, which is r double dot minus r times theta dot squared. Okay? So we have the mass. We could go ahead and do this number. 175 divided by 32.2. His mass is 5.43 slugs. Okay? So we're going to get slugs times acceleration in the radial direction is going to be feet per second squared. So slug foot per second squared is a pound of force. Okay, so it's going to be 5.43 slugs times the r double dot, which is minus 8t. I wrote that down wrong, didn't I? R dot 8. Here it is. R double dot minus 8 e. Sorry, this should be e to the minus t. Okay, I just did that incorrectly. Once again, I'm showing my own lack of familiarity with the nature of those derivatives. If I were doing this myself, I would have to get my math table and get that. If I were a student, I would have to get my CRC math table and break that out. Okay, so we have this times r double dot minus r, which is the original function, 8 minus 8e to the minus t. I'm just doing that so I just distributed that 8 through. I mean, there's no real reason for that, just that I did that, times my r function again. Theta double dot, which is this quantity squared. Okay? So if my theta double dot is, this is this, times this, that's my r. Whew, I'm going to lose it here for a second. I'm going to have to redo this because I just have too many things going on. So my acceleration summation force, 5.43 times the quantity r double dot, which is minus 8 e to the minus t minus r, which is 8, 1 minus e to the minus t, times theta dot, cosine of this quantity squared. All right? So then I need to work this out, and I'm at t equals 3 seconds, I think it says. Is that right? Yeah, so if t equals 3 seconds, we have 5.43 times negative 8 e to the minus 3 minus 8 times the quantity 1 minus e to the minus 3 times the cosine squared of pi over 2 times, I guess I could just put that as being 3 also. Okay? I have to remember that all of that's in radians when I take this number. Okay? So to work that out then, I get 5.43 times minus 8 over e to the third. I don't know if that's going to simplify or not. Minus 8 plus, I still have to multiply that. I should probably just get a value for that, huh? Eight times 1 minus the quantity e, 1 over e to the third. So I might have something that can simplify there. Now this is just going to be a number. So if I take my calculator and I put it in radians, so I'm switching to radians. What is switch? Enter. There we go. All right. So let's say, let's get back into my function mode. I have 3 times pi. So I don't even know where my pi is on this calculator. Uh, 3.1416. That's not going to be adequate.
Is the pi button second?
Where is it? Tell me.
Second, and then like the exponent above the division.
Yep, there we go. Thank you so much. So we got pi times 3 divided by 2. And I want to take the cosine of that number. Oh, it's not either. Oh, just the cosine, not the second cosine. Sorry. All right, so let's do that again. Jeez Louise. Second pi times 3 divided by 2 equals, I just need the cosine of that number. There we go. It's 0. Isn't that lovely? So that whole thing becomes 0. All right. So then, in other words, we have this. This whole thing becomes 0, doesn't it? That's nice. So we get 5.43 times negative 8 over e to the third power. So there's my e, the green button. No, that's a theta, sorry. There it is, second e, raised to the negative 3 times negative 8 times 5.43. All right, so I get that number as being the summation of forces in the radial direction equals negative 2.16275. And that value is going to be in pounds of force. Okay? So, and I've learned something new about my calculator. Thank you, Logan. So we're getting there. So then in the theta direction, the summation of forces theta is similar going to be equal mass times the acceleration in the theta direction. The mass is still 5.43. And the formula for the acceleration in the theta direction is r double dot minus r theta dot. No, I'm getting it mixed up, sorry. R theta double dot plus 2r dot theta dot. Okay? And if this is at 3 seconds, let's say r at 3 theta dot. This should be theta double dot at 3 seconds. R dot at 3 seconds and theta dot at 3 seconds. We're just going to see if we can simplify this a little bit. So my R value is 8 times the quantity 1 minus e to the minus 3. Double dot is negative pi over 2 sine pi over 2 times 3. And hopefully some of this is going to go to 0. R dot is 8 e to the minus 3. And theta dot is cosine. That would be 3 pi over 2. All right. So let's see if we go 3 times pi divided by 2, and we take the cosine of that. This is 0. Yay. And this, if we say, let's go the other way, sine of the quantity pi times 3 divided by 2 equals, this is negative 1. And so this is negative times negative is positive. That's pi over 2. And then here we get e to the minus 3 and we subtract that, so that changes sign, plus 1. That's wrong. Right, so let's go. 1 minus e to the negative 3 equals, and multiply that by 8. All right, so this quantity is 73.24, and this quantity is second e to the negative 3 times 8. So that...
You might be multiplying your e times the negative 3.
Say it again.
I think you might be multiplying your e times.
Oh, do you think I am? Yes, you're right, I am. It's too big. See? I got to use the cap button, don't I?
Or you can use like the second ln, there's like the e to the x.
Yes. See, right here. Okay. So let's go second e to the x.
And then you can
That got
take-
10, though. That took my 10 base. So I got the wrong one. Second e. There we go. Much better. Negative 3. That's a better number. Haha. And then I want to subtract that from 1. So this, and then multiply that by 8. So this is 7.60. Does that look better?
Yeah.
It does to me too. All right, let's do this one. And then we go second e raised to the negative third again, and multiply that by 8. And that value is 0.398. All right, so now we're able to plug this in. So we have r, which is 7.6 times theta double dot, which is pi over 2, and then plus 2. This one's here. I made that, that's r3 dot. Okay, that doesn't matter because this is equal to 0, plus 0, right? All right, so we get 7.6 times pi divided by 2 times 5.43. Okay, so that tells me that my F sub theta is 64.8, and that's also going to be in pounds of force. All right, now those are my components, right? So I know that this is this. I also know that they are mutually perpendicular. So if I wish to find the force in the resultant direction, I could 64.8 squared plus 2.16 squared. It's a negative, but it doesn't matter when you square things. So if I do, let's do this again. So if I do 64.8 squared plus 2.16 squared, I get a value of 4203. And if I take the square root, second square root, second answer of that, we get that the resultant force has a magnitude of 60. It's just barely over 64.8 because this is so small in comparison. And that would also be in pounds of force. It's 68.4. Okay, so this is one answer that would be acceptable, and that would be the other. Yes, sir?
When I multiplied the r times the theta dot dot,
Yeah.
I got 11 instead of 64. It's like 7.6 times pi divided by 2, right?
Let's see.
'Cause you have your r.
Which you're talking about this times this?
Yeah.
Okay, so r is 7.6, and theta double dot is pi over 2.
Yeah.
All right, so, and then this whole term
That one goes to 0.
is 0, right? Huh, okay.
So 7.6 divided by 2 is 3.8, and then times pi is like 11.
I may have, let's see, let me just take a look at this, because the numbers came out to be, the 64 is the same answer that your authors got. So, but I see exactly what you're talking about. So if I say 1 minus second e raised to the negative third, and I multiply that, okay, so I get that if I do 1 minus e to the negative 3, I get 9. That doesn't even make any sense. Clear.
I got like 0.95.
1 minus the quantity e, it should just be minus e to the negative 3 equals. So I get 9.
I think you're still multiplying by 0.3.
Oh, I am. See, you got to watch me every minute. Holy cow. Second log. So we're going to do e to the x negative 3. So that's 0.049, right?
Yeah. So
Multiply that by 8, and we get...
Well, it's supposed to be 1 minus the e to the negative 3.
Yeah, see how I am? Let's do it again. 1 minus second e to the x negative 3 equals. Okay, so 0.95. Multiply that by 8, and I get 7.6.
Which is what we had before.
Yeah, okay. So then... So I need to take that, that's my R value, and I need to multiply it by my theta dot quantity squared. And my theta dot is 0. So that should... It's the a sub r, a sub theta. Oh, here we go. See, my work is too messy to follow. So my a sub theta is right here. Okay, so I have if I solve for a sub theta, then is that the one that we're talking about? Yes, we're talking about r. Okay, so I have r, which is 7.6 theta double dot, which is pi over 2, plus 2 times r dot, which is 0.398. And that's the theta dot is times 0. Okay, so that goes away. So this whole thing goes away. So I have 7.6 times pi over 2, right?
Yep.
And that's what you're telling me. And then I get, like you said, 11. Oh, but then I have to multiply that by his mass. So the acceleration is 11.94, which means the force, which is equal to mass times acceleration, is that number times the 5.43. Yay.
64.8.
Yep, 5.43. And there you go, 64. So yes, that is correct. Whew. There's a little bit of math in that one. So lots of places to go wrong, lots of places to make casual mistakes. All right? So is that helpful?
Yeah.
All right. All right. We have 10 minutes left, which on a problem like this, we're probably not going to get a lot done. But do you have any others that you need set up or anything that I can do quick?
Yeah, I was confused on 12.76.
12.76. All righty. 7.3. All right, let's take a look at what we're doing. 7.6. Yeah, this one is an interesting problem because in order to set it up, we'll just do a quick setup and see if that's helpful to you. Okay, but basically what we're talking about is we want to take a look at okay, so here's the setup. It asks us, we observe that R has this function, R0 cosine theta. That's in the problem statement. we want to show that V is equal to V0 times the cosine squared of theta. All right, so basically, if you take angular momentum per unit mass, that is going to be equal to r squared theta dot. And that's going to, and so HO then is equal to R0 V0. Okay, this is sort of like the root equation. So if you solve this for theta dot, take this and set it equal to this, you get theta dot is equal to R0 V0 over R squared, right? Yeah. So then, from the geometry of the problem, you can see that because we're moving up from a semicircle, that R is going to be equal to R0 times the cosine of theta, right? Okay? And so R squared is going to equal R0 squared cosine squared of theta. So then you can do that, substitute that, R0 V0 over R0 squared cosine squared of theta, like that. Okay? Then, following this, we can also say that the velocity in the radial direction, just the velocity, is equal to r dot. So you can take the first derivative with respect to time of r dot, or of r, I should say, with r0 cosine theta. So if you take this first derivative, cosine goes to minus sine, so it's minus r0 sine that times the time derivative of the function, which is theta dot. And in the transverse direction, you can say that this is going to be equal to r theta dot. It's from those original equations. So you can take those two functions, differentiate with respect to time. Okay? And what you'll come out with is v sub theta is equal to r0 cosine theta, which is just r. You don't even have to do this, really. And then theta dot, which you've already found, which we can just call it theta dot here. Okay? And at this point, you can say then the velocity is equal to the square root of those two perpendicular components. And after some amount of manipulation, you will find out that it equals that expression. Okay? So in other words, this is going to come out to be r0 theta dot, which is r0 v0 over r0 cosine squared theta. And if you take, I shouldn't put that velocity vector, it should just be like that. If you take this, set it equal to this, and then pull out the v0, which you can find is this over this, then it's over that over the cosine of theta. So that's just a substitution. Yeah. Once again, it's pretty mathy. I really wanted to avoid, when we started talking about, I'm not sure, I'll explain myself. I don't know if it's the right way to think about it. But I didn't want to confuse angular momentum with the conservation of angular momentum and orbital mechanics. So I chose two problems that are very far removed from that. So don't know if that was really a good idea or not, but I didn't want to confuse those two issues. So, because I feel like the text confuses those two issues a little bit. So is that helpful?
Yeah.
All right. All right. Well, it was helpful to me. I know more about my calculator than I used to, so thank you.
Yeah, some of the versions of the software for these calculators are different.
Yeah.
But another thing that's helpful is just using the arrow key to find your old
Yes, so you could just click on that,
I
yeah.
upgraded to this other one and I can do that, but the other one I had, the old one, you can't do that. So you have to type all of them in.
I bet I could do it here too. I'm not that familiar with this calculator, so I don't know if it'll do it or not. It won't go up or down.
Yeah, you must have the older one.
I do. Dang it. Well,
But I think you could probably just download the software and install it.
that'd be great, so, yeah. So you squared away for everything?
Yeah, I
All
think
right,
so.
all right. Well, thank you. So like I said, no new material today, just this. And so then when we do dynamics lecture number 11 on Monday, we will start with chapter 13. So, and I think that the math in chapter 13 is actually quite a bit easier than 12. The angular momentum stuff, when you're not talking about under a central force, can get pretty strange. And especially RT coordinates are always a little bit strange anyway. So, but we'll talk about energy and momentum for system of particles in 14, and in 13 we'll talk about work and energy. The good news about work and energy is that work is a dot product, or energy is a dot product, so energy is a quantity rather than a vector. So you can start thinking about quantities being conserved instead of vector directions. So it's a little, the math is one, there's only one consideration instead of two. So, all right, well, thank you, and we will look forward to talking to you again on Monday.